1, 0 goes, and the second column represents where 0, 1 goes. This array of numbers is called a matrix, capturing the essence of a linear map. Another thing about linear maps is what it does to two-dimensional regions. Even though the region will be distorted, areas of any region actually scale by the same factor. In this example, this area grows by a factor of about 1.86, so for any region, the area also grows by exactly the same factor. This scaling factor is the determinant of the linear map. If the linear map involves some sort of reflection, for example in this case, we are simply reflecting along the horizontal axis, then even though the area hasn't changed, the determinant is -1 rather than 1, where the negative sign means our orientation has changed. As I said a minute ago, a linear map is summed up in a matrix, so we should be able to compute the determinant just from these 4 numbers. In fact, we can. In this two-dimensional case, we can compute by first multiplying the 2 numbers on the main diagonal, then minus the product on the 2 numbers on the other diagonal. However, this formula is not very crucial in understanding, so I'm not going too deep into it for now. Let's reduce to 1 dimension. As we said before, these 3 are the requirements of being a linear map. The first one isn't too relevant because we only have 1 line to deal with anyway. But the next 2 requirements mean that we are restricted to just scaling, so linear maps in 1 dimension are scaling. In 2D, the linear map is represented by a matrix like this, but in 1D, we only need to know where 1 goes, so the matrix reduces to just 1 number, which is the scaling factor. What about the determinant? Well, in 2D, the determinant is the scaling factor for areas, so in 1D, we replace areas by lengths, but the scaling factor for lengths is just the scaling factor in general, so the determinant is just that number inside the matrix in 1D. So we have what we need to know about 1D and 2D linear maps. What about derivatives?
My job is to make college easier because students have a lot on their plates. Like Harper, an econ major who piles on the pressure. Grammarly can help her stress less.
This term paper's gotta be great. It's a third of my grade.
Your ideas are on the money. Let's make sure they come across clearly with Grammarly. Watch it work. Watch it work.
Let's think of one-dimensional functions this way, transformations of the number line. So this is how squaring looks like. We are talking about a general function, so the spacings can be uneven. Now pick a point on the input number line, say a. Obviously, under the function f, it gets mapped to f of a, so what we actually want to know is the behavior of f on the neighboring points. So let's zoom into the neighborhood of the point a and observe what f does to it. It does look like a scaling, and in fact, the neighboring points are about 3 times apart. It's not exact, but when we zoom in even further, the discrepancy from this scaling approximation would gradually vanish. Here is a little technical remark. In general, the point A will move to f of a rather than just staying put. So in fact, we have been centering our perspective on A. This means that we can treat this as a linear map, well, sort of, because it's just approximately one. In this case, the linear map is represented by the matrix 3, because this is a scaling by a factor of 3. This is the Jacobian matrix at the point A for this one-dimensional function f, and the number in the matrix is the derivative, denoted f prime of a. In other words, the derivative is the scaling factor near the point A. It's important to note that this depends on where A is. If we have moved A somewhere else instead, then the function near A looks like this, and there is even some sort of reflection involved. Points on the right of the red points go to the left of it with a scale factor of 2, so we can approximate this with a linear map with matrix -2 and the derivative is -2. Even for the same function, the Jacobian and the derivative can be different depending on A. Similarly, for a two-dimensional function with two inputs and two outputs, we can visualize this using transformations of the coordinate plane. So this function looks like this. It doesn't look linear, and lines aren't even lines under the function f. But again, if we pick a point AB and then zoom in far enough, after centering our perspective on the point, it looks like a linear map. Again, this is not exact, but we can take the closest linear map approximation. This is the image of the exact linear map with respect to the original coordinate system. As discussed in the first chapter of this video, the matrix for this linear map should look like this. This is where 1, 0 on this coordinate system goes, which is 1, 1.5. On the other hand, 0, 1 went here, which is -1.
சார் உங்க இது அங்க ஷேர் ஆயிருக்கான்னு பாருங்களேன். அந்த லிங்க்ல இதுல நான் ஓபிஎஸ்ல பேசுறதெல்லாம் அங்க கேட்கலாம். நான் என்டையர் ஸ்கிரீன் டச் திரும்ப பிரசன்ட் பண்ணிருக்கேன். திரும்ப பிரசன்ட் பண்ணிருக்கேன். ஒரே நிமிஷம்